Okay, so this is going to be a presentation for the course, as I mentioned before. This is the course of dynamic analysis of irregular structures using OpenSeesPy. I'm going to be the main instructor for this course, and well, we are gonna have the help of engineer Julian Palacios and the bachelor's in engineer Daniel Medina. They are in the meeting too. So let's continue with the contents. So these topics that you see right here are going to be the contents for today's presentation. First, we're gonna take a look on what is OpenSees and what is OpenSeesPy. It's gonna be pretty fast. And then we're gonna go to the topics of the course. So we divided the course in 4 modules, which are algorithms in Python for those who are not very familiar with the programming language. So we're gonna see some of the basics, some algorithms also related to dynamic analysis. Okay, so it is going to be related to dynamics of structures. Then we're gonna start in the second module to see how we can model in OpenSees, how we can define a module, what methods OpenSees has, and stuff like that. Then in the second half of the course, we're gonna start to see some more complex analysis, which are related to modal analysis and response spectrum analysis. And this is going to be for an irregular structure. And finally, in the fourth module of the course, we're going to see the very expected nonlinear time history analysis. And this is going to be for the same irregular structure. Okay, so let's start first with what is OpenSees. So OpenSees, or the name OpenSees, means open source system for engineering or earthquake engineering simulations. So it says it's a system, but we can kind of think of it as a framework, and it is an open source framework for simulating the seismic response of structural and geotechnical systems. So I'm gonna maybe use this. Okay. So it is intended for simulating the seismic response of structural and geotechnical systems. You can also do, from what I know, you can also do or simulate fluids in OpenSees. So this is like the purpose of the system of OpenSees in this case. So it says it is open source, and when it says that it's open source, it means that unlike other software, maybe like eTapps or some commercial softwares, it is totally free. So it is a huge advantage of OpenSys, that you don't need to download or pay anything. You just can access and even modify the open or the source code if you want. So it allows you to do very complex analysis. You can do many kinds of static, dynamic analysis. You have a wide library with various kinds of elements, various kinds of materials also. So you can define the nonlinearities of the module. So it doesn't have like a disadvantage comparing to other commercial softwares. Of course, you don't have the advantage of maybe drawing or maybe the parametric modeling that some commercial softwares might have, but it's a very powerful tool for analysis. So we're gonna be taking a look later on what things you can do with OpenSys with examples. So, but I want to mention that it's a very powerful tool that you can compare it even with commercial softwares. Okay. So here's a timeline of the development of OpenSees and OpenSeesPy. So the first thing that came was OpenSees. So it was in 1999 where the developers of OpenSees started to code some algorithms. Okay, and in 1998, with the support of Peer, OpenSees was launched to everyone. Okay, so everyone could access to OpenSys in 1998. In the 20s, they implemented the tool command language as an interpreter for OpenSys. So it is not actually a programming language, it's a common language as the name suggests. But it works for you to run and create your OpenSys modules. So this is the basic or the standard way to create an OpenSys module. This was created in the 20s. Then OpenSys received the support from NESF, from the Network for Earthquake Engineering Simulations, and it supported the development of OpenSys. They started to create a lot of more materials, a lot of more elements, options in OpenSys. And it was in 2018 where they implemented Python as an interpreter for OpenSys. So as you might know, Python is a worldwide known programming language. It is used for many things from basic programming, machine learning, I don't know, web programming, any stuff that you can imagine. So since Python is very known worldwide, um, someone came with the idea of implementing it as an interpreter of OpenSys. So it doesn't have many years of implementation. It only has 7 years. So it's pretty new as you might think. And as an addition, I can mention that in 2020 they developed OPSVs, which is a module in which you can visualize your results of OpenSys of your OpenSys modules. So as you can see, it doesn't have many years of implementation. So they continue improving and improving OpenSys and the tools that you can use with OpenSys. Okay, so after viewing this very brief introduction on what is OpenSys and what is OpenSeesPy, now we can start to take a look on what we're going to see in the course. So we're going to start, as I mentioned, with algorithms in Python. So this is going to be we're going to be teaching or reviewing the basics of Python programming, the loops, the conditional statements, and so on, which are necessary to develop some modules in OpenSys. Okay, so we're gonna be also developing some algorithms in structures, dynamics of structures. For example, we have here an image. This is from Chopra, dynamics of structures. This is a single degree of freedom. Okay, this is an idealization, and we can make a lot of algorithms for a single degree of freedom. For example, here you have an animation of the response, the elastic response of a single degree of freedom due to a ground motion. Okay, so here you have animation, and here you have the ground motion record. Okay. You can have also the response of a multi-degree of freedom system. For example, this is the harmonic response or the harmonic vibration of a multi-degree of freedom system. Okay, this is in free vibration. And we're also going to take a look in the response spectrum. Okay, the response spectrum, and we're gonna see how we can build the response spectrum using Python, and maybe take a look at the design spectrum, how you can build it. Okay, once we have mastered the basics of Python programming, we can start to make our first modules in OpenSys. So the second module is going to be for totally modeling in OpenSeesPy. We're not going to use TCL. We are just going to use Python, and we are going to use Jupyter notebooks. We're gonna later show some Jupyter notebooks. And well, in the second module, we're gonna first define our first analytical module. Okay. And I highly recommend you to, when you create a module in OpenSees, first define the module in the paper. So you can kind of draw, you can define the frame or the structure you wanna model in OpenSees. You can define the nodes, you can define the elements, and you can define the connectivity between the elements and the nodes. So this is very important when you have more complex structures with a lot of nodes and a lot of elements. It is really important for you to don't get lost and the programming, on the coding of the module. So here's a simple frame, as you can see. The blue numbers are the node tags, and the red numbers are the element tags. And as you can see here, there is an OpenSeesPy module of this structure, and we have the node tags and now the element tags and the fits in the base nodes. Okay. So once we have defined our module, we can start to code it. Here you can see a basic structure on how you can module in OpenSees or in OpenSeesPy. So it's pretty similar to how you would define a module in any other software. So first of all, you have to import the modules here. For example, we have the OpenSeesPy module, okay, and the OpenSees module, which is for visualization. So first of all, I start here by defining nodes with its coordinates. Then we can define the material properties and the geometric properties, for example, for the concrete, the elastic modulus, the shear modulus, and so on. Then you can define the elements and its connectivity to the nodes. So you can define the start node and the end node for the connectivity. Then you can define the constraints of the module. For example, here in this case, we have a fits condition in the base. Okay. And this is everything, for the module. Then you can define the loads here. Okay, once we have defined the module, we can start by defining the loads. And you can have many types of loads here. You can have a nodal load at a specific node. You can have a distributed load at the element, for example. And you can have also static loads, or you can have dynamic loads that change in the time domain. Okay, then we can have this step right here, which I consider is the most important one, or one of the most important ones in defining the module, which is the analysis options that you're going to consider. So in this case, I'm not going to mention all of the options that OpenSees has here, but it has a lot of options, as you can see. So for example, we have the system method here that defines how OpenSees is going to construct the linear system of equations that we are going to solve. So as you might know, OpenSees and any other finite element software handles everything with matrices. So there are lots of equations, linear system of equations. So this is how you construct them. We also have, for example, the algorithm here, which states what algorithm you're going to use to solve that linear system of equations. For example, you can use a simple algorithm like the linear one. You can use the Newton-Raphson algorithm or any other algorithm that you might know for solving a linear system of equations. Other option that you might have is analysis option here. In this case, I'm specifying that it's a static analysis. You can also have a dynamic analysis, and other type of analysis that is in the documentation of OpenSees. Okay, so this is the basic structure with which you can define your module and run the analysis of the module. Okay, as I mentioned, this is one of the most important steps. And finally, you can have the results. For example, here I'm displaying or I'm printing the displacements of the nodes, and I'm printing the forces of the elements. Okay, so you can have also a lot of different kinds of results. For example, you can have reactions, you can have base shears. If you're working with fibers, with sections, you can have the stresses in the fiber. You can have the strains also. So you can have any kind of results you can imagine from your module. Okay, so that is how you can module an OpenSys. Then for the second half of the course, we're going to be taking a look at the model analysis and the response spectrum analysis. And this is going to be the structure for the course. As you can see, this is in the plan view. This is an irregular structure. Okay. Here we also have some other definitions like the material, which is the concrete, the sections for the columns and the beams, and the loads, which are area distributed loads. Okay, so this is the structure that we're going to handle until the end of the course. Okay, so you can make the modal analysis in OpenSees. So I'm showing here the vibration modes, the first 3 vibration modes of the module. In this case, we have the 2 first translational modes of vibration in X direction and in Y direction. And here we have the third mode, which corresponds to the rotational vibration mode. Okay, and here we have the periods of these modes. Okay, I think, yeah, I think Julian, we have an example to show for module analysis.
Yes, I will
Or
be sharing that in the course. Yes.
okay, at the end or right now?
Not right now. During the course. So this is an example where we can check the results of OpenSeesPy, doing some calculations in a node. Yeah. So it's to check.
Okay.
Yes.
Okay, so we'll be sharing the notebooks in the course. Okay, so let's continue. Once we have made the module analysis of the structure, we can start with the response spectrum analysis. So once we have the modes, then we can define the response spectrum. Okay, and we can get the response for each of the modes. Okay, so once we have the response for each of the modes, we can make the module combination, and you can use any of your preference combination, like the quadratic, complete quadratic combination, or any other combination that you know. And so this process is going to be implemented in Python. And finally, we can get the response of the structure, which is what we want. In this case, I'm plotting, or I'm showing the plot of a structure here. In this case, we have the drifts in each of the stories. Okay, in each direction, in X direction and in Y direction. In this case, we have drifts like around the maximum drift of 0.4 percent of 0.4 percentage, and you can get any other type of results in OpenSees. For example, as I mentioned, you can get I don't know, if you want to design a column, maybe you can get the maximum flexural moment or bending moment in the column. You can get the base shear of the structure. You can have the maximum displacement at the roof of the structure. You can have any result that you can imagine. Okay, so there was a third module of the course, and this is the very last module of the course, which is going to be aimed everything to nonlinear time history analysis. So in this module, we're gonna cover some important topics on some considerations that you might have in nonlinear time history analysis, such as the nonlinearities, the types of nonlinearities, damping in the structure, which is really important, how you can select ground motions and how you can change these ground motions, like scaling or modifying these records and stuff like that. So this is a summary on the nonlinear time history analysis process. So you basically use the ground motion as an input to the structure. So you need the ground motion and you need the structure definition, which is the same structure as before. And you can have some considerations. For example, in analysis, you might consider the nonlinearities, such as the geometric nonlinearities and the material nonlinearities. In the geometric nonlinearities, we might have the p delta effects due to gravity loads, which can be handled also in OpenSees. So OpenSees allows you to specify in what elements you need or you want to consider the p delta effects. Okay, and you can also define the material nonlinearities. So you can define the curve of the material. Maybe you have a concrete and you want to define the stress strain curve of the concrete. So you can specify some important points of the curve and you can define it in OpenSees. Okay, so once we run the nonlinear time history analysis, we can get the response of the structure. In this case, I'm showing another type of result we can get in OpenSees. For example, here we have the response history of the structure. As you can see here, we have the ground motion, and here we have an animation of the structure. It is scaled, so you might not see the displacement, but you can kind of see the displacement right now. So this was implemented with Matplotlib, which is a Python library. And you can also get some other type of results like hysteresis curves. In this case, I'm plotting the base shear versus the drift of the structure in the base, in the first floor. So as you can see here, in the hysteresis curve, there is energy that is being dissipated. So there is energy dissipation. So this can be related to the nonlinearity of the structure due to the ground motion. So you can have any type of results here. You can handle it in many ways. Here I am plotting it with a Python library, which is Matplotlib. But we can have any other type of visualizations. You can use ParaView or any other software for visualization. So OpenSees allows you to make complex analysis, but it depends on you what you are going to do with the results. Okay, so this covers everything about the topics on the course. We're gonna do a step-by-step process and in each of these modules. So we're gonna show show the Jupyter notebooks on each of these topics. So it's going to be a step-by-step process in the learning of the course. Okay, so now before finishing, well, now I'm going to show a code for give me a minute. I'm going to show the code of the nonlinear time history analysis. Give me a minute.
Uh, Sorry, Edson, to interrupt. Just to check, have you read the question in the chat?
Oh,
Let me read it. So, uh, there's a question, and it is, does the scope of our course also include nonlinear static and dynamic analysis?
well, the aim of the course is mainly in dynamic analysis, because static analysis might involve some other things, but maybe we can, yeah, maybe we can make at the end of the course, or we can aim some minutes of the course to some nonlinear static analysis with the pushover analysis. So yeah, if maybe the participants of the course are interested in an extra session maybe on the course for pushover analysis or any other topic, yeah, we could cover the static analysis, but the the aim of the course is mainly in dynamic analysis.
Okay, thank you.
Okay, nice. So I hope that answers your question, Mr. Sarif. And now I'm going to show the Jupyter notebook for this. I'm gonna change the presentation here. So please let me know if you can see my screen now. I think oh, maybe you can see my screen now.
Yes, we can see your screen.
Okay, nice. So now we're gonna take a brief look on this code right here. This is a Jupyter notebook. So okay. Okay, so first of all, as I mentioned, the structure of the OpenSees module follows the same structure. So first of all, you will need to import the libraries. In this case, I'm importing OpenSeesPy and OPSV's libraries for OpenSees, and I'm importing some other Python libraries for data handling. Okay, so first of all, before doing the module definition, I start by defining some base units here. It is a good practice to define your base units. In this case, I'm using meters, kilograms, and seconds as the base units, and with these base units, you can define any other unit that is derived from these ones. Okay, so once you define the units, you can now define a module. In this case, I'm gonna follow the same structure for the that I mentioned in the OpenSees structure as before. So here I start by defining the nodes. Okay, so I am using an Excel sheet here, and I'm gonna show it right now, which has nodes coordinates. So in this case, we have the nodes coordinates for each of the nodes, as you can see here. Okay, we also have the elements connectivity. So we have the I node and the J node of the start and end node. And we have finally the slabs. So these are the slabs nodes. So we have some quadrilateral slabs and we have some triangular slabs in the structure. So we just read that file and we define the nodes. So here's a plot on each of the nodes, as you can see. You might not recognize the shape of the structure right now, because it's just the nodes here. But later we're going to see how the structure looks. Okay, so then we make the constraints here. We're gonna constrain all the nodes in the base, all the translational and rotational degrees of freedom. So it's going to be fixed in the base. Then we can continue with the materials definition. In this case, as I mentioned before, we can define the natural material concrete and the natural material of steel. So these materials can define the nonlinearity of the concrete and the nonlinearity of the steel. So as you can see here, we're defining a lot of parameters which are going to help us to define the curve of stress-strain relationship. Then once we have defined the materials, we can start to define, in this case, the sections. Okay, since we are going to work with a distributed plasticity module in OpenSees, we have to define the fibers. So I'm not going to explain a lot on this code. This might be a little bit confusing right now, but we are just defining the dimensions of the sections, and then we define each of the fibers of the section. So in this case, the section, this is the column section. So we have confined concrete in the gray color, and for the yellow color, we have unconfined concrete. And the black dots correspond to the rebar steels. Okay, so we have our fiber divided in very, very small quads. And we can do the same thing for the beam. So we define the dimensions, we define the confined and unconfined concrete, so we can get this kind of a mesh. Okay, so later we can define the geometric transformation in this case. So this is for the geometric nonlinearity. So for columns, we are defining, or we're specifying that we are going to consider the p-delta effects, which are for the geometric nonlinearities. Just for the columns, not for the beams. Okay. For the beams, we just have a linear geometric transformation. Okay. Then we're going to do a beam integration. Okay. Which is intended for the distributed plasticity method. Since we are going to get the results in over all the frame, we are going to integrate the fibers. We're going to integrate the fibers in all the frame. So we're gonna kind of have like something like this, for example. We can have the column here, and we can have some fibers. Okay, let's imagine this is the I node, this is the J node. So we can have 5 fibers in a single column in which we are going to integrate. So that is what we specify here. So we have 9 number of integration points. Okay, and this works for the columns. This is for the columns, and this one is for the beams. Okay, that's how it works. I'm gonna clear. Okay, so now then we can start to define our elements. We have defined the fibers, we have defined the sections, the materials. Now we can define the elements and start to draw them. So here the only thing I do is define or draw the columns, and I draw the beams and that stuff. So with that said, now I can make a plot of the module, and this start to look a little bit more familiar to you. So you can see here the nodes, you can see the element tags, and you can see these red points right here, which correspond to the fiber sections I mentioned before, just a minute ago. So once we have defined the elements, another important step here that we have to do is define the slabs. Okay, and why do we need to define a slab in a seismic analysis? It is mainly because of the mass. Okay, as you might know, in a dynamic or in a model analysis, you need the mass and you need the stiffness of a structure to run the analysis. So the slabs are going to give you most of the mass of the structure. Okay, so this code right here might look a little bit of confusing here, but the only thing I'm doing here is defining the loads. Okay, the leaf load, the slab loads, and some other distributed loads. And this code right here, the only thing that does is to assign nodal masses to each of the nodes. So this code right here uses an approach. For example, here you might have a slab right here. So I, J, K, and L, for example. These are nodes of slab. So this code uses a finite element approach where this slab is the element, and this distributes the load or the distributed load to each of the nodes. So maybe if we have a total area here or a total load W here, it corresponds to this node, corresponds W divided by 4 distributed load. Okay, so we're going to assign this load, this area load to the node as a nodal load. So that's kind of how the this code works, and you can do this also for any kind of slab. If you have a triangular slab, you have 3 nodes, and you might you might have, for example, this. So you have this area which corresponds to the J node. Okay, so it works for any number of slabs. Okay, I'm gonna clear this. So that's what this code does. And after defining the nodal masses, we can start to define a rigid diaphragms and a center of mass, which is going to work for us for assigning the accelerations to the nodes later. Okay, so now we're gonna upload the module here. This is just an extruded view of the module. Okay. And now we can perform the module analysis. The module analysis is really simple here. For example, we have this block of code in which we just need to define the number of modes that we want to consider, and we can run the eigen method of OpenSees so that we can get the periods of we can get the periods of each of the modes. Okay, so then we can perform the gravity static analysis. Before performing the time history analysis, it is important to do the gravity static analysis because of the p-delta effects. As you might remember, we have considered the p-delta effects in our module for the columns. So in this case, we will first perform this gravity analysis. Okay, and in this case, I'm first defining the time series and the pattern, and I am assigning a distributed load for the columns and a distributed load for the beams. Okay. Then we're gonna reuse the code that we used before to assign the nodal load, but we're going to assign a nodal load to each of the nodes. Okay. So we're just reusing the code for the masses, for the nodal masses. Okay. Once we have assigned the loads, we can now run the analysis. And here I'm not going to dive into the analysis options. I'm just going to mention that we are using the Newton algorithm, and we are performing as an static analysis. Okay, So we can plot the deformed shape of the structure, and we can see here that it looks like a structure deformed due to gravity loads. Obviously, it is scaled. Okay, so that's why you have larger deformations, larger axial deformations. Okay, so after doing this gravity analysis, you can perform the time history analysis in this case. And first of all, well, I'm defining here in this block of code just the tags of the columns. It's not really important. Then we are defining here the ground motion. In this case, I am using a ground motion record from a research center from Peru. It's the Peruvian Japanese Research Center for Earthquake Engineering and Mitigation, Disaster Mitigation. So here, the only thing that I do is define an array for the time steps and an array that contains the acceleration value for each time step. So I'm plotting here the ground motion record, as you can see. Okay, this is how it looks. We have here the acceleration, and here we have the time in seconds. Then we can perform the analysis itself. Okay, so here in the first part, what we do is, well, first we have to wipe the analysis. This cleans the previous assignments for the analysis options. So it is important for you to clean the analysis options before running other analysis. And in this case, we are performing or we are assigning the ground motion to we are assigning it to the center of mass. Okay. And later we define the relative damping, which is a topic that we are going to cover in the course too. And well, I'm assigning here a damping ratio of 0.04. You can assign 0.02 or any other damping ratio that you might consider for the structure. And well, here I define the analysis options. The difference here is that the integrator method is now going to be the numeric method, which is for dynamic analysis. And the analysis is now going to be transient analysis. This means it's going to be a dynamic analysis. Okay, so then I'm just defining here some recorders for recording the outputs, so the results of some elements, as you can see. And now I can perform the analysis. So it's pretty simple actually. This is how you might perform a time history analysis, which goes from the current time step until the final time step. So you're just doing a loop, a while loop in this case, in which you can iterate or go in each time step of the analysis. So the reason why we have a lot of ifs and for statements here is because we have some we have a lot of tests and algorithms that we can use. So for example, you can see here that we have the Krylov-Newton method, the second Newton method, the Raphson-Newton method, and any other methods that you can consider for the algorithms. And you also have some tests that you can use to test the convergence of the module. So the only thing that this does is to check if the module has converged, and if it didn't converge, it changes between these algorithms and these tests. So after that, it's just going to get the results for each time step. I'm getting here the element force and the node displacements for some nodes. Okay. And I'm printing here each time step in each time. So that worked. As you can see, it lasted 86 seconds. And in this case right here, after we have run the analysis, we can get the results. Okay, so in this case, we can get, for example, the base shear versus the drift in this case. Okay, we can also get, for example, the time history or the response history of the displacement on the roof. And you can get any other hysteresis curve. For example, I'm plotting here a hysteresis curve for a fiber. So this is moment, and this is rotation for a fiber. So you can get any type of result that you can imagine here. And these are just some simple plots. You can make some other more complex visualization. As I have shown, for example, once you have run your model in OpenSees, you can have some other more complex visualizations. You can make animations. For example, I'm going to show you here an animation for the base here. Okay, so for example, this is animation for the moment curvature of an element here. Okay, you can also have this animation right here, which is for the response, the total response of and the displacement of the structure. And you can have any other type of visualization or results that you can imagine. And I want to finish with this reflection, which is that OpenSees is just like a tool. So it's not like it can replace an engineer maybe. It's a tool. It's a really powerful tool, but it depends on the user. In this case, it might be you. What you're going to do with the results. So you are going to define the model. You are going to define whether it's a static analysis, a dynamic analysis. You are going to also decide what are you going to do with the results. Maybe you're going to use it for some research purposes. Maybe you're going to use it for I don't know, for design of structures. It is really powerful also for structural analysis and design of structures. It might be pretty fast for those purposes. And you're going to decide what you are going to do with the result. So that is my final reflection. It is just a tool, and you are going to decide what you're going to do with the tool. You're going to decide the engineer and the mechanics of the structure. Okay, so that is my final reflection on this presentation. And I don't know if maybe you might have some questions. We had a question before. Okay, maybe you might have some final questions and maybe the contents of the course or any other topic that is related to the course. You can let me know.
Okay. So maybe if they are writing, so in the meantime, there's a question. What is the schedule of this course? Yes. Well, regarding the schedule, let me reply to that question. Yeah, the course schedule is every Saturday, in the same time that this webinar has started. 10:30 in Lima. India, I think it's 8 9 p.m. in India time. Saturdays. Yes, that will be the time schedule. And it will be through 6 weeks, I think, Edson. Is it right?
We're gonna go with 5 weeks actually.
5 weeks.
So
Okay.
yeah, it's 4 weeks. Yeah, 4 weeks are going to be with the topics of the course, and there is a final week which is for the presentation of a final project. So the participants on the course um should present a final project on the topic. It might be anything related to dynamics of structures. So but obviously using OpenSeesPy. Yeah, it's going to be 5 weeks.
Okay. Nice. Okay. If there are other questions, please write it down. And yes, well, also I want to do a final comment as well. So from my point of view, yeah, like nowadays researchers are using OpenSees, not OpenSeesPy, but they are using OpenSees. Sometimes OpenSees can be a bit difficult using the call command lines, but with Python that is much more easier. So I think yeah, that's OpenSeesPy is very simple comparing to OpenSees. And nowadays, yeah, some people can argue that Python can be a bit slow, but it helps to understand. And that's why like nowadays many people is using also OpenSees because they started learning OpenSeesPy and then they learn OpenSees as it as the typical command lines. So yes, and for example, I've been reading there's research on uncertain quantification of uh, structural responses and also some sensitivity analysis using OpenSees uh, analysis of structures, and there are a lot of research on that. So this is very useful, and as Edson said, it is just a tool for analyzing structures. And there's another question, Edson. Let me read it. How about the necessary installations? Will there be a guided installation in the course?
Yeah. Well, I didn't mention that. I'm using right now Visual Studio Code here. Maybe you might have seen it before. But we are not going to be using Visual Studio Code in the course because you need to install Python, then you need to install Visual Studio Code, install some libraries. So the participants on the course might have some problems with installation process. Actually, we are going to be using Google Colab, which is it is yeah it is delivered from Google, so it's cloud stored, and you don't need to install anything. So you just need to create a Google account, which is totally free, and you can have access to lots of Jupyter notebooks on Google Colab, which is the same thing as having the files I'm showing right here. So these files can be run in a Google Colab file, which is a Jupyter notebook as well. So there is not really a necessary installation um, since we are going to be using Google Colab. But we are also going to teach how you can access Google Colab, how you can create a Google Colab file and dive into the options of Google Colab. So we're not going to be using VS Code because it might be difficult to some participants. So I hope that is good for you.
Okay, thank you for the answer, Edson. So yeah, and yeah, this the code that Edson explained today also will be shared in the e-learning platform of the API. And if you are not enrolled yet in this platform, you can contact the API directly in the WhatsApp group. So just okay. So if there are no more questions, I think we can finish this presentation. Well, thank you very much, Edson. Very nice presentations and also the examples and all the videos that you prepare. Thank you for that. And so see you next week in the course.
Okay. Thank you too, and thank you for coming today to the webinar. See you the next week.
All right. See you.